Testing, testing. Is it good for you guys? Yeah. All right, let's start. And then today is the last day of the lecture. And then I just want to cover the final course review, but some of the students would like to learn more about the operating system. So like I told you about, I will introduce a little bit of the modern operating systems, but unfortunately, I was too busy. So I couldn't, I just slept 2.5 hours and then came back to the class. But that does not justify teachers never prepare some of the more things to the students. So I prepared a little bit of slides about introducing some of the how virtual machine works, and then please enjoy those slides. And then at the end, I will go over the final course review. Yeah. So let's start. So you guys are working with the QEMU and GDB for debugging an operating system. Yeah. So we use debugging a lot to implement the operating system because for even JOS is around 8,000 lines of code. So, and compared to the Linux or Windows, that kind of the real operating system, which consists of several millions lines of the code. So for example, Linux comprises of around 20 million lines of code. So the complexity of the operating system is totally order of the magnitude much more bigger than the JOS operating system. So without that kind of debugging, don't ever think about debugging the Linux with the printf in your brain. And then if you do so, then you're super genius. Yeah. But otherwise, I highly recommend using GDB all the time. And then you guys have seen that I'm keep repeating the for some of the questions, I'm going to keep repeating the attach GDB, and then let me know about the instruction pointer. Then we can locate where the bug is. And then for the first few times, you guys may think using GDB might be wasting of your time if you can figure out the error easily with some of the workaround. But as the complexity of the JOS implementation goes up, for example, left 4. And without GDB, it's very hard to triage and then fix the error. So this kind of debugging feature is essential, but have you thought about how we can debug the operating system? So for example, if we run an application and if we debug that application using GDB, then there's an operating system below, and that manages both GDB and the application. So it works perfect. But to think about it, so in our structure of the computer systems, the CPU runs the operating system. And then we are developing the operating system. Then what if my operating system has a bug? Then it will stop at some point. Yeah. And for example, if the triple fault happens, then CPU will stop and reboot. So right now, every time there's a triple fault, what you guys need to do is press Control A, X, and then make QEMU no X again. That's it, right? But without that kind of the QEMU, GDB, that kind of thing, every time you have a kernel triple fault or something, it will reboot, then they will enlarge your development time, increase the development time again and again. So it is so painful. Then think about, so now we have a QEMU or that kind of the virtual machines, so we can easily debug the kernel. Then how was it before the era that we have lots of virtual machines? So there's some of the old-fashioned way of the debugging the kernel is that. So think about it. We have a CPU, and then only software that we run on top of the CPU is the operating system for the developing of the bootloader or that kind of thing. And then if that fails, there's no software we can run debugger on it. So there's no one on the CPU. Our CPU stopped with debugging the operating system, so that will never work. So how old-fashioned way works is that for the hardware designers, some of you guys are from EE background or something, I'm sure that you guys have heard about the JTAX, the Joint Test Access Group. So what it means is it's somewhat standard for the chip testing. Let me mute it all. Thank you. Yeah, chip testing. And then what does it mean is that like it's a hardware debugger for the integrated circuits. And then our CPU is also IC chip. So what it means is that, so this is a recent NVIDIA sum of the board kind of thing. And then it has a CPU, and then there's a sum of the port here. And then that port is called JTAG. And then if we connect some of the lines here, then it will directly talk to CPU. So if the CPU stopped, even if the CPU stopped with the bug from the operating system, and there's another interface that we can talk to the chip directly to get the information about the fault information, such a thing. And also we can set the breakpoint at the CPU. Yeah. Then that provides a little bit of debugging features. And then our GDB can talk to this kind of the protocol. Then we can control the CPU so we can debug. So the JTAG kernel debugging, what it actually do is we are connecting some of this kind of the old line, and then there's a converter that this kind of the serial connector to the universal serial bus, which is USB. So it's something like there's a CPU target device via JTAG. We can connect that, and then we can connect the USB to one of the computer machine. Then you can run GDB on there to debug this kind of NVIDIA board. Yeah. And then this was how like we do in kernel debugging in old era. So what kind of drawbacks will be there? So if suppose we don't have a QEMU, then we need a real device to do the kernel debugging and connect the JTAG. So maybe some of the other courses in the EE, I may require you need to purchase that kind of board to take this class, but thanks to QEMU, we don't need to spend that kind of money. That's the, so all the way, we need a physical device. And then that means in this kind of the pandemic scenario, can you work remotely? Yeah, no, yeah, that's another problem, yeah. So even if like we can technically forward all the USB connections over the IP, so we can technically use some of the USB device in my home country, South Korea, and actually that can be forwarded to over the IP and then connected to here. But that is overkilling technology, I believe, yeah, for this kind of a class. So so in short, in the old era, like we have to use a JTAG USB and then tied into the physical machines, and then that generates lots of headache on the kernel debugging. And then another headache is that whenever there's a triple fault, and then you have seen lots of this kind of screen, then it will be rebooted. And then reboot means like a power off and on. Yeah. Or some cases, not even like not on the Intel CPU, it could just stop. In that case, suppose some of the cloud service purchases this kind of devices and then serving remote debugging, there could be that kind of services. Then if there's a halt, like this halt of the CPU like that, then what we need is this kind of the Samsung small things outlet, then we can remotely turning off and on. But I'm talking about some of the old era. In that era, there's no such devices at all. So now we can say thank to QEMU. So whenever it halt, stop, just take 1 second. Kill it, run it. So we run QEMU as an application. So that's why we can run those kind of the entire just kernel and your user application and then entire virtual hardwares on the OS2 server as a Ring 3 application. So I'm talking that like we are writing a code for Ring 0, but now I'm talking that all your jobs was running in Ring 3 on our OS2 server, which is somewhat IRA, but let me describe how that actually works. So this kind of the QEMU or the other things, like QEMU is a quick emulator. So these are so-called virtual machines. So virtual machines is a computer, but it's a virtual environment that works like a computer. So you can think it as you wrote a program. It's just a Ring 3 application. And then you create the x86 CPU struct and then put all the EAX, those kind of registers, CR3 or that kind of thing. And then you can create that kind of software to read the kernel code instruction by instruction. Then it can interpret the code and run it. So that's basically how the virtual machine works. So to run these kind of the instructions, so one way to run it is like directly running on the Intel CPU. Otherwise, we can, because we know the semantics of each of the instructions, just read one line and then do what it does in the CPU and then mimic entire those things as same in the software. That's basically how the virtual machine works. And then we use QEMU. So the QEMU is a tool of the generic computer emulator. And then it implements software CPUs, something like this. Yeah, there's a software CPU, and then they can read and then run all the instructions. And then another benefits of like running this is that it can run many virtual CPUs. So if there's a definition and then implementation, software implementation of the virtual CPU, then QEMU can run Intel 3264-bit, PowerPC, ARM, Spark, RISC, and then many other architectures. So yeah. So for example, most of you are using either x86 computers or newest Mac uses ARM CPU. But suppose you want to analyze some of the operating systems on your Wi-Fi router. So your Wi-Fi router is actually a computer, and it runs mostly Linux. Yeah. And then the CPU of it is sometimes it's a MIPS processor because it costs just $1 for the CPU kind of thing. Yeah. And then if you want to take a look at the software, you can actually do that. Just take QEMU, set it to use virtual MIPS CPU, then you can boot that Wi-Fi router operating system on your desktop or any kind of server. Yeah. That's the basic concept of the QEMU. So we use QEMU for support of virtual debugging. So OS2 server has an Intel CPU. Yeah. So don't have to be Intel CPU. We can actually run JOS on iPhone or anywhere. Yeah. If there's a QEMU, yeah, it's like you can run QEMU. So the Intel CPU on OS2 server runs QEMU that has a virtual CPU. And then that virtual Intel CPU runs JOS as a ring-free application. And then on top of it, because it has a virtual CPU, QEMU implemented debugging feature on top of the virtual CPU. That means it opens the network socket, and that's why sometimes you run the multiple instances of QEMU, then bind address already in use, something like that. The reason is like the script automatically gets your user ID and then generate the unique number, and then open the port that GDB can connect to the QEMU to talk with the virtual CPU for the debugging. And then because this is just a software on the server, yeah, there's no restrictions on the running remotely, then that's how like we can do the kernel debugging and that kind of development remotely and conveniently. And then let me give an example of what QEMU can do. So this iPhone runs as an ARM CPU. So you can compile entire QEMU in ARM architecture. Then in that QEMU, you can select to use a virtual Intel CPU. Yeah. Then the result is you can install the Windows operating systems on the iPhone so that you can do whatever you want in there. And then another thing we can do is, have you seen this kind of thing? So this is a touch bar of the Mac. And then, so the implementation of the Apple devices, like there's a Intel CPU or ARM CPU, but there's another CPU called Apple T1 or T2, which is also being used by the Apple Watch kind of thing. So that is inside this touch bar. So that has specific architecture, but if you can run QEMU or slight lower level virtual machine, something like a DOSBox kind of thing, then we can run any kind of game. So this is a famous game in my kid age, the Doom. Yeah, so it's quite a meme that whenever a hacker hacked some of the computer, even if if that is like not an Intel architecture, then like the hackers leave running the Doom on it and then just left away. That's some of the famous Frankenstein meme. So you can do this kind of thing here using QEMU. So one of the example is that some of OSU Sec Club students and I visited DEF which is a hacking conference in 2019. And then there was an event at the voting village. And then there were lots of voting machines were there. And then our students go there and then hacked voting machines and then played some x86 game on it. Yeah, even if that was not the architecture of the x86. Yeah, that is so fun. Unfortunately, our students found the vulnerabilities on the specific machine. And then that machine is prevalently used by the Georgia or other states. Yeah, so I don't believe like the election was rigged or something like that, because like to hack the machine, the people need to be in physical and then open the machine and then plug the USB device. So it's somewhat the physical hacking kind of thing. Yeah, but it's true that some of the voting machines are like having the vulnerabilities like that. Yeah. The important point is not about the election and the voting. The important thing is like you can also do more other kind of games on the voting machines using QEMU. Yeah. Then, what is the virtual CPU? So maybe I always remind you guys about what is the beauty of the computer science, is that it's not about the natural science. We are not challenging to the nature. We are working with something that's human built. That means if it is an open source, we can take a look at the entire implementation. So how I study about the computer is that, so I want to share the kind of the things to you. So whenever I'm curious about how QEMU implements the virtual machine, then search GitHub, search CPU, and you will get to the CPU editor. Inside there's a struct. It's just like a regular C program. We are implementing a virtual CPU, has a registers, VIP, flags, and also LDT, GDT, something like that. And then whenever the instruction sets GDT, then we change the values here, something like that. So if we know how Intel CPU works correctly. So have you actually looked at if you actually look at some of the instruction description of the Intel CPU, there's a pseudocode. So what QEMU developer did, try to interpret like that kind of thing, and then just move that into the software, and then running the CPU, and also peripheral hardwares. For example, QEMU also emulates a console, keyboard, network, those kind of thing. Yeah. So that all those things in the software, yeah, and it works well. And not just for the this kind of the architectural state. So it also implements internal structure of the CPU, for example, L1 cache, L2 cache, yeah, those kind of things can also be determined in purely software, so that you can actually virtually orchestrate the hardware that you would like to use. And then another thing you can do with QEMU is like, suppose there are many instructions of the Intel CPU, but suppose you want to implement a new instruction, and then would like to test if that speeds up your 3D game or something like that, or it can protect some of the memory or speed up some of the mechanisms. Then what you can do is, so do you guys know how long does it take like actually creating one CPU to tape out? So we need to send the code to the fab, and then it will be printed and get back. So at least it will be taking like the 1 week, and then nowadays like the pandemic made all the deliveries so slow. Yeah, so it takes us several more weeks. But with QEMU, you can directly test all the things. So actually, some of the performance characteristics would be totally different in hardware and software. So that you cannot measure the performance, but at least you can test the correctness of your new instruction introduced, something like that in QEMU. So that means even if like you want to modify the hardware, so you can virtually do that, all the experiment in QEMU, and then make sure that you do not have any kind of bug, then you can actually print that as a chip, something like that. So that we can use this kind of software to engineer the CPU also. And how this QEMU works. So I told you QEMU runs a virtual CPU. So it totally runs in Win 3. What that means is that you can regard that this machine is an OS2 server, and then this is the OS kernel, which is Linux on top of it. And there are libraries, and then we run QEMU. Inside of there, we have a virtual CPU here. And then this virtual CPU just accepts kernel.object, then just read and interpret. That's it. And then JOS runs inside of here. But let's take a look at what would be the JOS's perspective of the rings and then how the hardware is connected. So JOS runs here, but it's actually inside of here. Yeah. So JOS believes it directly talks to the real hardware, but it's all fake. Yeah. So you can think it as like the operating system will ask something, then as software, if they say exactly the same thing what hardware says, then we can actually emulate the hardware environment. So that's how QEMU do. And the QEMU not just emulate CPU, it also emulate graphics, disk, network, and other devices, and then all the things running in Ring 3. And then how it runs is that we have a virtual CPU here, and then suppose these kind of the bootloader code comes in, and it goes to this one, and then you can think it as like something like Python. You just interpret instruction by instruction, and just run it. Then we can actually see the operating systems, not just the JOS. We can also run Windows 10, Windows 11, or other operating systems, any kind of thing in QEMU. So that's how it works. So if you just take a look at the output, then it looks super complex, but the core design of the virtual machine is very simple. Virtual CPU and just interpret that. And then emulate all the hardware, mimic all the same input and output. Yeah, something like that. Then can your Ring 0 JOS in QEMU kill the operating system to server kernel? So my question here is that to point that, so JOS runs in Ring 0, but that is Ring 0 in QEMU. And then from the perspective of the operating system kernel on OS2 server, it's just Ring 3. So they can never touch the memory area here, except for dealing with the system calls. Yeah. That's the thing. And then Ring 3 in QEMU is just Ring 3. Ring 0 in QEMU is also Ring 3. Yeah. So that they cannot touch it. Then how can they protect Ring 3 and Ring 0 in QEMU? That they also need to virtualize page table structure to check if there's a PPU for every time memory access goes to there. Yeah. So virtual CPU need to emulate all the behaviors of the CPUs. So if the CPU is too complex, then it requires a significant time to implement the virtual CPU. But once it is done, then we can freely use them. So there are lots of pros and cons. So pros are technically we can run any kind of program in any architecture on top of any real CPU. Yeah. So Apple drastically changed their CPU from the Intel x86 to the new ARM CPU, but there is no problem of like running the previous x86 compiled binary on ARM machine. And then how that works is so-called the Rosetta 2. Yeah. And then I believe like the reason why they use like the name the Rosetta is like the stone of the translation, right? Yeah, it's just translating all the x86 instructions to the ARM instructions. Yeah. And then that's very similar to QEMU. And then QEMU is just a naive one. It was a naive one, just interpreting all the thing. But due to the performance reason, it has been developed a lot for applying the just-in-time compilation. What that means is that suppose you have a block of assembly line of the x86, then we actually using compiler to compile this into the ARM code and then just run. By doing that, speed of the thing will be much more faster than QEMU kind of thing. So if you use QEMU for running an application, you will see that your applications will be 2 times slower or something. But with the just-in compiler QEMU or Rosetta kind of thing, you will see that around the 20 to 30% performance down in there. Yeah. So the conservative part and the cons part is like the slow because like it implements all the things in the software. So and then also it goes by instruction, but we can remove that kind of restriction with the just-in-time compilation. So the reason why it's called as a just-in-time compilation is that we don't compile entire kernel code, but whenever we need certain snippet of the code need to be translated, then we do that, compile and run it, compile and run it. And then there are many other virtual machine implementation, and then QEMU is just a naive one. So you have heard about VMware, Parallels, Hyper-V, Zen, yeah, those kind of things, VirtualBox. And then all those things are virtual machines. And then the critical difference between the QEMU and these virtual machines are, QEMU does not require hardware support the virtual machine, that kind of thing. So that's why QEMU purely runs the software, so it is slow. And then these virtual machines would have 1 or 2% of the performance overhead on top of the bare metal machine when it's running on the other operating system, something like that. Yeah. So how do they speed up that much? So I told you, like, if we do it purely software QEMU, and then 2 times slower, but how can it be like just 1% or 2% slower? Then let's take a look at how it works. So I'm sure that you guys are all familiar with this kind of diagram. So it's a user kernel separation, and then we learned about the syscall IRIT kind of thing. And then how does virtual machines with the hardware extension works is that we put another layer below the operating system. And then we started with the ring 3, ring 0. Unfortunately, there's no more positive or non-negative integer number, so we have to use ring -1 because it's below the level of the ring 0. And then ring level means that there's a memory protection. That means hypervisor will directly talk to all the hardware, memory, CPU, all the things. And then operating systems to talk to with hardware, they need to be mediated by the hypervisor. So that you can think it as, so the application is there, and then operating system mediates between the hardware and the ring 3 software. Same thing happens. Virtual machine, hypervisor ring -1, that mediates the communication between the hardware and the operating system. So that you can think it as, in the perspective of the hypervisor, operating systems are applications. Yeah. And then in the perspective of the operating systems, applications are just applications, something like that. So you can think of that kind of nested architecture. So if we run multiple operating systems on a hypervisor, so you will see something like this. So we previously have seen that, I have shown, if we run multiple applications on the one operating system, so there will be multiple applications. So the same thing, one hypervisor, we can run multiple operating systems, like this kind of thing, application. And then how this operating system then talks to this kind of hardware. And then one hint is that we already learned about for an application to talk to operating system, we use system call. Interrupt, syscall, sysenter, these are all the mechanisms to get into the operating system. And then IRIT, sysexit is the opposite side, so it gets back to the ring 3. Same thing happens, but the name is much fancy. VMexit, VMenter. Yeah. I believe like so this kind of mechanism is developed in old CPUs, and then Pentium 2 implements the sysenter and sysexit, and then AMD 64 in 2003 implemented syscall and sysread. And then, then this is also implemented by AMD first as AMD B in 2006, and then they named it as a VMexit and VMenter. And then VMenter means it's like from the hypervisor, we are getting into the operating system. VMexit means operating system requests something to the hypervisor. So that you can think it as a VMexit as a system call to the hypervisor. So we actually call that as a hypercall to distinguish this from the system, regular system call. So ring 3 to ring 0 is a system call. Ring 0 to ring -1 is hypercall. So that you can actually see some of the analogy or similar structures of the hypervisor operating system and the application. So yeah. So once you learned about this kind of architecture, I believe if I just not showing this kind of the diagram, and then if I just throwing the questions about like how you can design the virtual machine kind of architecture, then I believe that you guys can also think about, because we did it like this right here. So you guys can also easily think about the BMX, BMenter kind of design. Yeah. And then how to interrupt, how do we handle hardware interrupts in this kind of the architecture? So previously, if the packet comes in, then packet goes to the operating system directly, then it will be delivered to the Win3 application. But it has a one more layer, so it goes to the virtual machine and then goes to the operating system and then user. But because having one more layer means that there's an additional overhead on accessing the hardware. So to speed up the virtual machine for the hardware access, for example, network devices or like and then performance critical graphic cards for the FPS game kind of thing. Yeah. So one of the technique is that we can remove this kind of layer. So if the administrator configure it correctly, then we can actually forward one of the device directly to the operating system to remove this kind of link. Then the performance of that hardware access from the operating system will be the same as the bare metal operating system, because we just removed additional layer specifically for that hardware. But unfortunately, so if we do so, one of the problems is that, so I've shown this kind of diagram to you guys. Then we run three operating systems, and then they will all share these hardwares. So if the Windows sends a packet, it will send via this network. Mac sends the thing, and it will send the same hardware device. But if we pass through this device to the one specific operating systems, then it is captured, owned by that operating system, so that cannot be shared by the other operating systems. Yeah. So if you take a look at the Amazon AWS cloud configuration or something, then depending on the network speed, your cost of the virtual machines is a little bit different. And then for the super fast hardware, they require this kind of a pass through and then pass through. And then if they do pass through to your virtual machine, then that device is occupied by you. That cannot be shared with the others. That's why it is a little more expensive, because you are occupying the device. And then to support this, x86 CPUs implemented the VM extensions, and then AMD introduced this as a so-called SVM. Yeah. And then Intel calls it the VM extensions. Yeah. And then basically it creates a new layer, not just for ring 3 and ring 0, ring minus, and then put the hypervisor on it. And then you can regard VM exit as a get into the hypervisor hypercall, and then VM enter as the getting out from the hypervisor to the operating system. So you can feel that kind of the structure. And then another interesting point about this kind of the virtual machine is that, think about it. Suppose there is a memory, and then that physical memory can directly access by the operating system previously, but we have a layer of the hypervisor. And now hypervisor directly works on the physical memory. And then operating system runs on the virtual memory of the hypervisor. And then ring 3 of the data operating system runs virtual memory of the entire system, which is the virtual memory of the operating system. Yeah. So how do we call each of the memory? It's something like this. So the real physical memory is so-called host physical memory. So hypervisor manages all the host physical memory, and then operating system can deal with the guest physical memory. And then that's actually virtual memory and the perspective of the hypervisor. Yeah. And then ring 3 runs as a guest virtual memory. Yeah. That's the real the meaning of the nested virtual memory. Yeah. So, and the problem of having that kind of the memory structure is that if there is so think about it. So we have a guest, like the virtual memory in Ring 3. And then it will be translated into operating system. And then that will be also translated to the hypervisor. And then current architecture of no, not the current architecture. Current architecture can support this kind of extended page table. So CPUs without having extended page table. So we have not learned about that thing. So that you can think about the current JOS is just using the 2-level page table. But if it is a 64-bit, we only have a 4-level page table. So you can think it as not just 2-level, 1, 2, 3, 4. So we need to work down 4 times, then we can access the memory. Yeah. But think about it. Hypervisor, operating system. Between these two, we have to use page table because if we let the operating system contaminate the hypervisor memory, that's the security violation, and then isolation is not completely tight. So what we need to do is we need to have a virtual memory layer there. So we have to use page table structure between the hypervisor and then operating system. Then we also need the virtual memory for between the operating system and then Ring 3. And we only have one CR3. And how can you put the nested virtual table, page table? Yeah, something like that. So that was challenging. And then how original virtual machine implementation in 2004 and 2005-ish was like just use regular CR3 page table for between the hypervisor and the operating system. So this kind of translation is done by hardware so fast as if like just a bare metal operating system. But between the translation between Ring 3 application and the operating system, it is managed by purely in software. So in that era, virtual machines were too slow. So both Intel and AMD engineers. So in 2008, there's no, I believe the Amazon Web Services just started around that era or something. So I believe like around the 2005 to like 2015, that was the golden era of the cloud computing. Yeah. So most of the companies are focusing on the virtual machines and this kind of techniques, and then reducing the overhead. Actually, turns out they can reduce the server cost, and then all the benefits, they can benefit from that. Yeah. So how Intel and AMD designers, hardware designers implemented this is that, so they actually created extended page table. And then what that means is that, so first, so you will have the Ring 3 virtual memory. And then it goes to the translation to the virtual to physical. Yeah. Then that physical memory is the virtual memory of the operating system. Then that needs to be translated as a physical memory again. So how it works is that, so this is the CR3 from the operating system. Yeah. Then it walks down, so that this is the CR3 of the Ring 3 of the guest operating system. So we need to walk down 4-level page tables, but to get the physical address of this CR3. So this CR3 is on the Ring 3. Then that physical address is the virtual address of the hypervisor. So we need to translate that 4 times to get the physical address of the top-level page table. And then to walk down another level, we need to walk down 4 more times, and 4 more times, and again and again. So 1, 2, 3, 4, 5 times of memory access to get the physical address. And then 1, 2, 3, 4. So we need was it like around 20 times of the memory access to get the virtual to physical memory translation. So it was 2-level in 32-bit CPU. And then it was 4-level in the regular 64-bit CPU. But if we want to get into this kind of extended page table, that will be 20 times. But then you might think like 20 times is too much, right? Too many. And then it could incur like lots of overhead. But the interesting thing is that implementing these purely in software is more than 100 times slower than this. So right now, page table translation on the virtual machines, not just go for the 2 steps, it goes for this kind of the 4 multiplied by 5, so 20 times. And then in these days, 4-level page table can only support like around, what is that? 256 terabytes of the memory. To use the more memory, they implemented 5-level page table. And then if you run the virtual machine on the 5-level page table, and then 5 multiplied by 6, so 30 times of the memory translations are involved. Any questions up to this point? No, was it good to understand? Yeah. So if you can understand the similar architecture of the ring 0, ring 3, and ring 0, then ring 0 and ring -1, then it'll be easy to understand. And then a little bit of the complex thing is something like this, and then think about it, how the ring 3 application memory needs to be translated as a ring 3 translated physical address and goes to the operating system, something like this. Yeah. And then another interesting thing is like right now QEMU is developed as an open source, and then QEMU is actually developed by one guy. Do you know that? Do you know this name? I cannot speak French, but yeah, Bob I don't know, but this guy is a genius engineer. And then so some guy calls that like this guy is a Japanese in France or something. And then some of the magnificent outcome of his software is like one of the funny things is JS Linux. So this guy developed QEMU. So he ported the QEMU on JavaScript. And then if you go to this side, then you can run Linux entirely on Chrome. Yeah, something like this. And then you can think of it as like a JavaScript runs a QEMU and then run the operating system, something like that. And then this guy also developed the FFmpeg. So have you ever converted like a video format in one to other? It takes too long time. Still too long time, but before having the FFmpeg, it takes too long time. And then this guy hated that, just implemented for a few nights, and then FFmpeg was the state-of-the-art speed of that. And then another thing is like, have you heard about the IOCCC? It's a international obfuscated C code contest. So it's something like a weird C code and then bragging about the eliteness of their coding skill or something like that. And then this guy implemented a 100 kilobyte compiler. And then compilation speed of that is around 9 times faster than the GCC, which was the state-of-the-art compiler. Yeah. Then that is a 100 kilobyte in binary. And then that composes around the 75 kilolines. But to compare that to how much of the lines in the GCC is several millions of lines, then this guy can implement a better one with the lower lines of the code. And then we cannot directly compare this and that, and the GCC has lots of other parts, but 70-something lines of the code is too small for the compiler. So and then I just want to introduce like the QEMU is awesome. Like one guy developed the entire like the first version, and then yeah, it is developed by one of the geniuses. All right, then for the rest, I will go over the recap about what we have learned for the entire term. Yeah. So we have learned the several topics starting from the boot, virtual memory, and the user kernel switch, and preemptive multitasking and scheduling, thread synchronizing and scheduling. And let's go over one by one. So in week 1, we learned about how operating system boots at the start. So how x86 processor boot with the BIOS, so which mode the processor starts with. Now we know the answer. The processor always says on the real mode, and then addressing model in the early stage of the booting is a segmentation, then the address multiplied by 16, then add the offset. And then BIOS loads the boot sector, and then that is loaded as 7C00, and then that's fixed. So the one of the exercise asks you to change this kind of address, and you cannot boot because CPU expects that all the code is located at 7C00. And then how boot sector loads the kernel is that boot sector directly talks to the disk hardware and then parse the ELF header and then load the kernel according to the section header information written in there. And then we have two modes of the processors. So it starts with the rear mode, and then it will be turned on with the protected mode. And then in protected mode, we need to use GDT to specify what kind of memory, what kind of region we can access with the within the protected mode. So in week 2, we mostly focus on the memory translation. So from the segmentation in real mode, segmentation in the GDT protected mode, and then we have a paging. So paging is one of the way to implement the virtual memory. So paging is not the only way to implement the virtual memory. There are so many ways, but empirically it's performed well. So we are stick with the paging. So that there are several academic researchers that saying that the page table is not that efficient design. Yeah. So that kind of research is also interesting, but still in using the page table is the de facto standard of the implementing the virtual memory. And in doing that, 2-level translation even incurs like a 2-level of the access of memory, then that is much slower than the access memory in the cache. Accessing from the cache is this cycle 1 cycle, and then from the memory, 200 cycles. Yeah. So we can cache those kind of translation, and then that buffer is called a translation leukocyte buffer, TLD. And then whenever we update the page table, because TLD is not synchronized that, so TLD is inside the CPU, and then page table is inside the memory, so there is no link between these two. So if you update this, then this still remains there. So whenever you update the page table, then we need to call IMVLPG, that's the instruction name, the TLD invalidate. Yeah. And then in week 3, we implemented the virtual memory layout. And then after you implement the boot map region, you know how to set the memory readable, writable, user, that kind of thing. And then based on this kind of the memory layout, you implement the entire virtual memory layout for the jobs. And then we need to manage the translation of the page table. And then that requires accessing of the page directory and page table. And then page is 4 kilobyte. And then in 32-bit CPU, 4-byte pointers are used. So all the entries are 4 byte. And then we have a 1024 entries. So that's why we can index those in 10 bits. And then I introduced that the page table structure is a little bit different in 64-bit. The biggest difference is that their pointer size is 8 bytes. So we only have 512 entries. So that each of the level can consume 9 bits. So starting from 12 bits, 9999, 36, 12, that's why 48. And then if we add another level, 48 plus 9 is 57. So 5-level page table can support up to 57 bits. Yeah. And then we can also like arbitrarily set like this kind of thing. And so if we reduce the page size, and then number of bits could be reduced or enlarged. So that kind of things also like some of the design factor of the systems, but nowadays we are just stick with this kind of thing. So yeah. And then in week 4 and 5, we learned about the user kernel switch and then ring structure. Yeah. So this is how operating system protects the system from the potentially malicious software. So that even if the malicious software try to like access the hardware directly, that is not possible. And then it is always mediated by the operating system via system call. And then how we switch the execution from the user's kernel is the system call, IRIT, and then now you guys also know that VM exit, VM enter. Yeah. This is how we switch between the rings. And then the ring levels are stored into the last 2-digit bits of the CS register. So like if you implemented the page fault handler for the kernel or something, you have seen like this code snippet for checking kernel or user, those kind of thing. And then, so another thing to notice, like now you guys know what is the difference between the library call and the system call. So the library call is something like a printf, so that you need to implement some part of the printf in the user space. And then at the end, it will actually call system call syswrite. So there will be a structure like the ring3 application code, library code, and then system call. So to invoke the system call, we can use these kind of instructions. And then to return back to the application, internally in JAWS, we use EMB poptf, but the specific instruction that does that is iwait. Yeah. And then to support this kind of the user kernel switch, we need to implement all the interrupt handlers because we implement the system call via interrupt handling on 030. Yeah. So you can set the interrupted descriptor based on the interrupted descriptor number, and then the handlers like this. And then based on what kind of error number, or with ring3 should be allowed or not. So we can set some of the values like that. And then one of the important questions here is that for some of the data, when interrupt happens, some of the data are automatically stored by the CPU, and then some other additional data need to be provided by the operating system. And then to easily identify which interrupt number it is, because CPU will never store the interrupt number. So that's why we created the handler for each interrupt number, and then it will put the interrupt number by the operating system. Yeah. So if there's no assembly code that actually store that kind of information, then those informations are coming from the CPU. Yeah. And then after that, we work with the interrupt, and then you have seen lots of this kind of trap frame. Then this kind of the trap frame information is the information exchanged between the user and kernel. So that whenever a user wants to enter to the kernel, user need to deliver their context to the kernel, so that kernel can know which system call do you want to call, or something like that. And then not just for that kind of system call, if there's an error, for example, page fault, then we can identify what kind of fault it is. It says user read not present. This means that there's no valid page table entry there. Yeah. And then what is the faulting address? From CR2, yeah, we can identify that. Yeah. So null pointer reference. Yeah. So from this kind of trap frame, we can see lots of information. So there's an IP, and then we can figure out which line of code is problematic, and so on. So there's some of the students asking me a question during like Android Lab 3, and then showing that trap frame, and then I don't know anything. And then, so most of the time, like I was on the cell phone, and then I just reply, check your curry EMV or check or something like that. And I actually didn't take a look at the code. And then just look at the trap frame, I can see that. Because it has a lot of information about this kind of things. And then at least, I don't know what this program is. At least I know that, oh, this is a fault happening from the user. Because the address is the user program address, right? And then null pointer address. Or you guys have seen like some of the value of the 54 or something. That's the sum of the struct member of the curry EMB. Yeah. So that's why, like, if I see the 54, then I can tell you about like a check pop EMBTF for the take a look at the current EMB, something like that. There's no magic. Yeah. So just take a look at the trap frame. You can see lots of information about that. And then if you have not finished the lab 4, then please try it like me. Yeah, just taking a look at the trap frame, you can figure out know the problems. And then if you cannot figure out the problem, then easiest thing to do that is just set the breakpoint over here. Frame EIP, then that's the problematic instruction. And then you can see that which part of the code is generating the problem. And then we can also check like which ring level it is based on the last 2 digits of the CS register. So 1B, this means 11. So 11 plus 16, right? And then the last 2 digits is 3. So that's why it is from ring 3. And then we also learned about how we handle page fault. And then one of the tricks that we learned is like that we can implement the copy on write design, which does not involve a lot of memory copy when we do fork, yeah, or like the sharing the memory pages. Yeah. And then the important thing is like the page fault is a fault. Yeah, it's an error. But the beauty of this kind of fault handling is that we can handle the fault, and then we can exploit that kind of fault handling to implement either copy and write or memory disk swapping. And then we can make it that is totally transparent as a user level application. In their perspective, they don't know if it is a copy and write, or they don't know this disk swap. Yeah, maybe they can measure the time of the loading of the memory. So if it is already in the memory, the access will be fast. If it is copy and write, then it involves memory copy, so it'll be slower. If it is disk swap, then it's much more slower. So that there are some of the security problems that you can apply side channel attack based on that kind of the timing. Yeah, you can see that which part of the memory is already up or down. Yeah, so that we can see the internal structure of the operating system, but without that kind of the information, there's no direct access, or you cannot observe if you're just running the user level application, then under the hood runs transparently. Yeah. And then after finishing the virtualization part, and then we move up to the concurrency part. And then if you run 2 or more threads at the same time, then there could be chance that there will be data race. And to avoid that, we need to use one way to do that is using the mutual exclude. And what that means is that we can implement conceptually lock and unlock. Log is get into there if doors is open, and then close the door immediately. Then I'm the only one in here, then get out, and someone else can get in. And we can use the logs like this. And then critical section is defined like this. And then only one thread can enter that among the thread who would like to acquire log. We also go over like several lock implementations. So if you implement the lock in purely software, then that will never work. So there's a hardware instruction to support the lock that was exchange. And then drawback of that is like it was keep changing the value, even if the previous value is 1. And then that has like some of the cache invalidation issue on the multi-core CPU. So in single core CPU is totally fine. And multi-core CPU is problematic. So there's a concept of the compare and exchange. But the problem is that unfortunately Intel didn't implement it well. So we can implement it in pure software with the using exchange, or we can also apply the exponential backup. So that's how we can engineer the lock makes faster and also reducing some of the contention. But these are not only the problem. If you use the lock incorrectly, we could have some of the concurrency bugs. So the definition of the concurrency bug was like if you run it as a single thread, there's no bug at all. But if we run it with the 2 or more threads, then there could be a problem. So one of the example of that was like the time of check to time of use variability. So time of check, yes, it is not null. But in the middle of that, if we set it as a null, then this line will be the null pointer reference. But in single thread application, there will be no cases like that. Then another severe bug is that if you use the log incorrectly, then there could be a case of the deadlock. And then we went over the several cases that how we can remove the deadlock. Was like a remove mutual exclusion. It's like do not use lock, use exchange, compare exchange, the primitive directly. And then hold and wait is like if there's a two locks. And then if you acquire the first one, fail to acquire the second one, then there could be a problem that all the threads that would like to acquire the second one should wait for it depends on the acquiring the lock one and lock two, the both of them. And to remove that, one way is like we can apply the meta lock to make the entire locks acquired and released simultaneously, or we can implement the try lock and then release everything to get back to the thing. And then to avoid like some other problems, we can order the locks, and then to make it that kind of order, you should not rely on the variable name, that kind of thing. So you should rely on some of the unique identifier. Then you can compare the values with the total order. Yeah. So we use a pointer because in virtual memory is a 1-to. So virtual memory, and then virtual memory itself is unique. Yeah. So that's why we can use that to order some of the locks. So you have many things from the operating systems from this course. And then I've been hearing that students saying that this is the most difficult course at OSU. And then is that true? Then I don't want to make give an impression that this is a really difficult class. And then it's difficult because like you guys never experienced about like this kind of intensive debugging, and also usually a lot of applications don't say about the triple fault, and then there's no double fault, those kind of things. But that's kind of the conceptual thing, because you have not been seen that kind of under the hood. Yeah. So it's new. So in 10 weeks of the schedule is quite intensive. But I would like to praise all you guys. Yeah. No, I forgot the word. Yeah. So I just want to say that you guys did it very well. And then you guys not only survived during the pandemic and also survived from this kind of the most difficult class. Yeah. And then please keep doing well until the Lab 4 deadline finishes. Yeah. And then you learned how to build your own operating systems with the knowledge of the x86 as an internals. And it's not that great, but at least you guys have learned some of the important fundamental things of the operating systems. And then another thing that I would like to tell you is like if you're curious about how Linux works, then just go to the Linux kernel source code repository and then take a look at some of the source code. But surprisingly, what you will feel is that some of the code looks exactly similar what JAWS has. So actually, JAWS is developed by MIT, and then so MIT was at that era like the best in the operating system, and it's still there. And then these guys are super elite hackers on the Linux kernel, and then because they are from the Linux kernel side, they designed to JAWS to mimic some of the things and the syntaxes in there. So it's intentionally developed as a pedagogical operating system, but it's real, and then it's tried to show most of the real things of the real operating systems. Yeah. So we learned about how the operating system boots, virtual memory, interhandlers, system calls, locks, page fault handler, copy and write, and then in Lab 4, you guys handle with the preemptive multitasking and multi-core CPU. So please be confident after you finish this class. Now you know many of the internals of the operating systems. So not just for the operating system design. I know it was painful, but I intentionally make all you guys use Emacs, Git, Vim, like lots of that kind of tools. So some of the students were struggling a lot because they had no experience of using the tools, but I intentionally would like to do that because when you finish the degree and go for work, then these are some of the standard tools to use. And then I want to make all you guys be prepared about that. Yeah. So it's okay to tell me about I cannot handle merge conflict, but please don't do that at your work. Now you know how to handle that. Yeah, that's what I felt. Yeah. And then another thing is like one thing to notice, like I promised that you guys to like I will post this, I will give some of the example interview questions and answers, those kind of thing. And then I couldn't prepare that right now, but I will upload that slide and then share that to you. So you can link some of the interview questions and then something that you learned from this class. And then next time you do interview, then you will be much confident about the answering to some of the questions related to the computer systems. So for example, one of the questions that my student received from the VMware was, have you experienced a kernel level programming? Then now we can say, oh, it's not the real thing, but with the pedagogical operating system JAWS, I have implemented starting from the bootloader and then loading the kernel, implementing physical virtual memory management, implementing page table, and then you can tell about lots of details of that. Then the interviewer will see that you're not just like a regular student, then somewhat outstanding student in the computer systems. Yeah. Yeah. And then I'd like to thanks to some of the heroes to make this class finish as well. So I want to say thanks to like all our TAs, and then you guys also get a lot of help from the TAs too, right? Yeah. So please thanks to TAs. And then I also thanks to like the students who actively engage to the Discord. And then someone who asks the questions, someone who replies to the questions. Yeah, all these like the thread and then the dialogues, they will be definitely helpful for all the other students. And even that is even helpful for me, because from the things that you are asking, I'm keep updating my course material to reduce the number of the questions. So that I would like to improve this class again and again. Hopefully, I would like to match some of the top school standards. So they do teach just left from 1 to 5, and then they do some more, even in 10 weeks at the University of Washington. And I hope that someday like that I can teach everything at OSU without getting the name of this is the most difficult course at OSU or something. Yeah. And then also who survived for the JOS labs, even if you cannot finish lab 4, I know that's difficult. Yeah. You have never experienced that kind of multiple like that. It's concurrent the environment. So even if you cannot finish lab 4, yeah, you guys achieved great things that you have implemented your own operating system. And then there was one extra adventurous student, and then he or she actually offered me that if he or she can implement JAWS entirely in Rust in his own way, and then if I can grant all the credits to him, yeah. And I said yes, and then he couldn't finish some of the IPC or something like that yet, but he will finish that until December 10. And then I'm also like very excited about like that kind of like extra adventurous work. So you guys had like a stuff of the skeleton code. It's totally different. He developed the entire thing from the nothing, and then works like JAWS. Yeah. So maybe in the next time I will offer the class, and then I would like to get another group of those kind of the adventurous students to build a more exciting project about that. And then I would like to say another special thanks to this student, James. Yeah, he's the real hero. Is he here? Yeah, yeah. Can you send the big applause to it? Yeah, you're the hero, and then all my TAs that think that usually TA work hour is 3 hours a week, but we know that TAs are doing professional debugging. They're actually working 30 hours, 40 hours, and then even I worked there like around the 40 hours, and then last time I go for the course, and then department has said they never do that again because I cannot do research at all. But I really enjoy like dealing with the student and then teaching. Yeah, so that's why I did that. But James, thank you all. You saved lots of our time, and then and also lots of students get benefit from your answers. And then another thing is like So another thing is like if you study something and then if you teach that to someone else, then you will learn a lot. And then how I see about James is like he was not the perfect student at the first place. He also asked me a lot of questions. And then after learning from me or other TAs, then he delivered his knowledge to the other students. And then you guys also benefit from there. And then some other students also pay forward for the what they have known and then what they have suffered for the others. Yeah. So we helped each other and then survived during this pandemic. So I thank you to all of the students and yeah, thank you all. And then another thing that I want to show is that this is one of my PhD students. And then he entered OSU in 2019, a spring semester. And then his background is in mechanical engineering, and then he don't know about coding. And then the first class he took is my class because he's advised by me. Yeah, I forced him to do that. So at the end of the term, now he code like a pro. And then now Jin Hong can help you guys with a good sense of the debugging, right? So if you do that and train yourself with the debugging and then play with the many other programs, then you will also be good and for this kind of the operating system stuff. And then another thing that I will announce is that the students are saying that I keep lowering the grading brackets. Yeah, but I would like to help you guys during the pandemic. So I will accept the all year left 4 assignments till December 10th with the 100% points. So please work hard till the end. Please get as much as point you can get. Yeah. And then another thing that I want to tell, last thing, is that your JOS is the real operating system. If you bake it to the USB, you can actually boot on your machine. But the problem is that that's the 32-bit processor, so you need to limit the physical memory to the certain size. Then it will actually work. So please try it. So you can actually boot the machine on the real computer. But if you're not sure about your JOS would screw up with some of the disk or something like that, yeah, then you need to use some of the computers that not the thing you're actually using. So there's a spare computer, and then you can actually boot your operating system and see that your operating system runs at the real machine. That would be fun. Yeah. So please be proud of yourself. So you guys all finished a lab. Most of you finished the lab with a great score, and then most of the students got a perfect score on the quiz. Yeah, I'm really happy with that. Yeah. So yeah, this is all. Yeah. And then I forgot to answer one of the students' question during the Zoom. So where does hypervisor could live are there options for which hypervisor I can run on my machine. So you can just think it as hypervisor is also an operating system. Operating system that can run operating system. Yeah, so something like that. So hypervisor is stored at where operating system usually stored. And then another interesting thing is the hypervisor may be used for protecting another systems because there's another layer of the isolation. So starting from Windows 10 or something, if you are not running any kind of virtual machine on your Windows, then Windows 10 automatically takes the so automatically inserts a very thin hypervisor. And then the reason is that some of the malwares hacks the Windows kernel and then get into the hypervisor. Then that's called the blue pill attack. Do you know the blue pill and the red pill in the movie Matrix? Yeah. So if you take the red pill, you can get out of the thing. But if you take the blue pill, then there's a malware that you will never know what's going on in the hood because you will never access ring -1. So that kind of thing happens. So the Windows 10 just take the position of the hypervisor at the first place and then run the operating system. This is one of the way to kill the blue pill attack, but there is a way to work around it. Blue pill ++ attack, maybe. Yeah, that's also possible. So even if the system designers didn't well, there are always ways to hack, because I'm more on the hacker side than the operating system design side. Yeah. So that is, yeah. Then, right. Yeah. Then it goes over 3 minutes, so you guys feel free to leave. So this is the end of the class, and then thank you all for your effort, and then feel free to come down and ask the last questions. Yeah, you have. Thank you.